Okay, for problem 1.10.6 on page 123 of Modeling in a Real and Complex World, I'm asked to find and classify the equilibrium values of the recursion equation given below, and then describe the long-term behavior with the initial condition of P0 is equal to 50. Now, before I jump right into it, I noticed something about this equation that I remember from the reading, and that's that it looks like a logistics equation. So in other words, it fits very closely, or actually exactly, to the model P sub n is equal to some rate times 1 minus P sub n minus 1 divided by a carrying capacity times P sub n minus 1 plus P sub n minus 1. And I remember from the reading, this type of model was first introduced on page 111. And R is going to refer to my rate of growth, and C is going to be some carrying capacity, or in other words, a max capacity that I would expect my system to hit under normal growth conditions. And C in the reading is an equilibrium value. That carrying capacity, I expect that to be an equilibrium value. So now I'm going to go into what I'm being asked to find. First, I'm going to find the equilibrium values. And again, from my intuition, I suspect that since C is equal to 1,000, that 1,000 is going to be an equilibrium value. And I also remember from the reading that 0 is an equilibrium value for this type of logistics equation. But let's solve it algebraically to verify that that is correct. So if I'm looking for an equilibrium value, I'm looking for a value such that when I substitute it in for P sub n minus 1 on the right-hand side of the equation, I get the same thing back out for P sub n on the left-hand side of the equation. So algebraically, I'm going to replace all my P sub n's and P sub n minus 1's with P star. And I'm going back to the original equation, where I actually have the numbers. Okay, the first thing I'm going to do to simplify this is I'm going to subtract P star from both sides of the equation. Okay, now I'm looking for that P star that's going to satisfy this equation. And I notice that on the right-hand side of the equation, I have 3 terms multiplied together. Now, if I could make any one of those terms 0, then I'm going to get 0 on the left-hand side of the equation, and I will have solved for P star. So my first term is this 3. I know I can't make that 3 equal to 0, so I'm going to move to my second term, which is 1 minus P star over 1,000. I'm going to try and set that equal to 0. So 0 is equal to 1 minus P star over 1,000, or P star over 1,000 is equal to 1, or P star is equal to 1,000. So that looks to me to be an equilibrium value algebraically. And when I look at my initial form, the general form of this logistics equation, that makes sense to me because I remember that this C value, which was 1,000 in my particular equation, is an equilibrium value. So now I'm going to look at this third term, just P star. Well, that's easy to set equal to 0. I just set P star equal to 0. And again, if I set P star equal to 0, then I've got 3 times 1 minus 0 over 1,000, or 1 minus 0, times 0, which does equal 0 on the left side of the equation. So both of these equilibrium values look good to me, and the common sense checks out with the form of the logistics model that I have. Now I'm asked to classify the equilibrium values. Now to classify them, I'm going to look back at theorem 1.10.1 from the modeling in a real and complex world, and that theorem is going to tell me the conditions under which these equilibrium values are either attracting or repelling. I'm going to use it, theorem 1.10.1 first, using some calculus, and then I'll show you how you can do it without calculus. But so first, theorem 1.10.1 says that I need to take my recursion equation as a function of p sub n minus 1. And it's important that this is a recursion equation and not a difference equation, meaning that we want all of our p sub n minus 1s on the right-hand side of the equation, and then just p sub n on the left-hand side of the equation. So if I look at this as a function of p sub n minus 1, it's going to be equal to 3 times 1 minus p sub n minus 1 over 1,000 times p sub n minus 1 plus p sub n minus 1. And I'm going to start grouping like terms and simplifying. So 3p sub n minus 1 minus 3 over 1,000 p sub n minus 1 squared plus p sub n minus 1, or 4p sub n minus 1 minus 3 over 1,000 p sub n minus 1 squared. Okay, now referring back to the theorem, I want to take the derivative of this function with respect to p sub n minus 1. And I'm left with 4 minus 6 over 1,000 times p sub n minus 1. Now, to evaluate the stability of my equilibrium points, I have to evaluate the derivative at the equilibrium point. So let's start with p star is equal to 0. And I have f prime of 0 is equal to 4 minus 6 over 1,000 times 0, which is just equal to 4. Now, referring back to the theorem, since the absolute value of this is greater than 1, or in other words, 4 is clearly greater than 1, then I know that p star is equal to 0 is repelling. Now I'm going to look at p star is equal to 1,000. Again, I'm going to evaluate the derivative at 1,000, which is going to be 4 minus 6 over 1,000 times 1,000 is equal to 4 minus 6, or negative 2. Now I take the absolute value of negative 2, and since the absolute value is 2, which is greater than 1, again, p star is equal to 1,000 repels. So now I've classified both of my equilibrium points as repelling using calculus. But if I didn't know the calculus, I can go back to this general form of my recursion equation. And this is where it was good to reflect on the problem a little bit before I started to solve it. Because if I refer back to page 120 of the book, I see that for this form of the equation, f prime of 0 is equal to 1 plus r. Now I know that r is equal to 3, so I get the same answer from above. It's equal to 4, again, which is greater than 1, and therefore p star is equal to 0 repels. And it should not surprise me that I got the same answer that I got last time. Now let's look at, again, page 120, and let's evaluate our derivative at c using the equation that's given straight out of the book, which is just equal to 1 minus r. Again, substituting 3 for r, we have 1 minus 3, which is equal to negative 2. And since the absolute value of negative 2 is equal to 2, which is greater than 1, p P star is equal to 1,000 also repels. And again, it should come as no surprise that regardless of how we did it, we got the same answer. So now I've both found and classified both equilibrium values. I'm asked to do a third thing, which is describe the long-term behavior with initial condition of P0 is equal to 50. Now, to describe the long-term behavior, I'm going to refer back to the textbook again. On page 120, it mentions that with an R value of 2.7, the system exhibits chaotic behavior. In this case, our R value is equal to 3. So it's even greater than 2.7. So I suspect that this is going to be a chaotic system. And that sort of makes sense as well when you think about us having two equilibrium points, but both of them being repelling equilibrium points. So if you were to look at page 118 and figure 1.38, based on my value for R and the two repelling equilibrium points, I would suspect that our graph would look very similar to the graph in figure 1.38 if we were to do a time series plot. Now, I would encourage you to go to Excel and you will verify that this is indeed the case if you iterate out your recursion equation, starting with initial value of P naught is equal to 50 and P sub n is equal to 3 times 1 minus P sub n minus 1 over 1,000 times P sub n minus 1 plus P sub n minus 1. You'll see that this is a divergent system, and moreover, the long-term behavior does not approach positive infinity or negative infinity. Instead, it just randomly and erratically oscillates. So to describe the long-term behavior, we would say the limit as n approaches infinity of P sub n does not exist, and DNE stands for does not exist. And again, I would really encourage you to look at Excel to verify that that is the case. You can take it all the way down to the bottom of the Excel spreadsheet, and you'll see that the value for P sub n never settles upon any value. It just erratically oscillates.